Hello and welcome to part 2 of this series introducing the Hodge star operator. So in this second video on the introduction of the Hodge star operator, we will focus on its properties and demonstrate its use through several examples. All right. Now, so the Hodge star operator provides a way to transform a K form into its complementary n minus K form, as we saw in the last video. So in R3, for instance, the Hodge star operator can be thought of as transforming a line element into an area element, or vice versa, depending on the dimensionality of the form. Now, this is useful in connecting different geometric quantities, like relating flux through a surface to the circulation around a boundary. The Hodge star operator helps to express duality in geometric and physical problems. For instance, in electromagnetism, the electric and magnetic fields can be described by one forms and two forms, and the Hodge star provides a natural way to switch between these descriptions, capturing the intrinsic relationship between electric and magnetic fields in a sort of unified framework. Now, in physics, especially in theories like general relativity, electromagnetism, the Hodge star operator is crucial because it provides a way to move between different descriptions of the same physical phenomena, ensuring that equations and concepts can be consistently translated across different dimensions. All right, so we need to have a look at how this works. All right, some properties of the Hodge star operator. Its duality. So the operator establishes a duality between K forms and n minus K forms. So for instance, in R3, one forms, which can represent directions or lines, are dual to two forms, which can represent areas or planes, and vice versa. Okay, so I mentioned a bit of that on the previous page. Involution, double starring, double use. On an n-dimensional manifold, applying the Hodge star twice gives star of star omega, or Hodge star of the Hodge star of omega, minus 1 to the power of k n minus k, k times n minus k in parentheses, times omega. Okay, this property implies that the Hodge star operator is an involution, meaning applying it twice returns the original form up to a sign. Okay, it'll return the original form, but up to a sign. That's, okay, so positive or negative. Linear transformation. The Hodge star is linear, meaning for K forms, omega and eta, and scalars AB, the Hodge star of A times omega plus B times eta, in parentheses there, is just equal to the Hodge star of each one separately. The Hodge star of the sum is equal to the Hodge star of the individual parts. All right. Next one, introduction with exterior derivative. So for a K form omega, the exterior derivative d satisfies d of star omega, or Hodge star omega, is equal to the Hodge star of the exterior derivative of omega. Okay, so they swap places there. This relation plays a crucial role in the formulation of Stokes' theorem and other integral identities. So the exterior derivative of the Hodge star of omega is equal to the Hodge star of the exterior derivative of omega. Okay, Hodge duality and co-differential. I'm not really going to get into this part. I really just put this here for completeness, if you like. But the co-differential delta is the adjoint to the exterior derivative and is defined using the Hodge star. So delta omega is minus 1 to the n, dimension n of the space, times k, the degree of the form, plus 1 times omega. For K forms omega, this operator acts as delta is an operator that maps the space of K forms to the space of K minus 1 forms. All right. I won't do any more on that here. All right, so let's have a look. So let's consider an example. So let's have a look in R3 with the standard Euclidean metric. That's the diagonal matrix with ones in the diagonal. Let's find the Hodge star of the one form, omega a dx plus b dy plus c dz, basis one forms dx, dy, dz, and constants or scalars a, b, c. Now the two forms star omega, Hodge star of omega, is given by Hodge star of omega is a dy wedge dz minus b dx wedge dz. And that's, go back to the first video, the video prior to this for why that is, wedge dz, plus c dx wedge dy. Okay, that's the Hodge star of that. As I say, go back to the previous video to see what it is. Now let's verify First thing we'll need to verify all this is the volume form, vol subscript R3. Now, say our manifold is R3, and the volume form in R3 is dx wedge dy wedge dz, all covered in the last video. And using omega and eta equal to omega, and we'll have omega wedge star omega, Hodge star of omega, is this wedge with this, because remember this is the Hodge star of this. Okay, well, expanding that out, we're going to have a dx here, wedged with that 2 form here. And when we do that, we get a squared, a here, a squared dx wedge dy wedge dz. Notice here, a dx wedged with this bit here doesn't make much sense because dx wedge dx is 0. And same with the third term here, dx wedge dx is 0. So I've not included those in order just to free up space. Otherwise, we're going to have a lot more terms if I expand each one of these with each 2 form here. Okay, then we go to the next one. So we have b dy wedged with, well, no point doing it with this one because dy wedge dy here is 0. And over here, b dy wedged with this over here, there's a dy here, dy wedge dy is 0. So the only term that's non-zero, b dy wedged with minus b dx wedge dz. So we get minus b squared, b from here, and the b from here gives us b squared, dy wedge dx wedge dz. Okay, and then the last term here, c dz in the first parenthesis, last term c dz wedge, well, there's a dz here, so there's no point wedging that, it'll just give us 0. There's a dz here, so there's no point wedging it with that because that will give us 0 as well. So c dz wedge c dx wedge dy, so c here and c here gives us c squared. We have dz wedge dx wedge dy. Okay, we'll have a look at this now. So the volume form is dx wedge dy wedge dz, so let's get it into that form. So here we need to make a swap. Dx needs to move here, so that's a single swap, so that changes the sign. We'll get plus b squared here, dx wedge dy wedge dz. Here now we're going to need to move dz 2 places, 1, 2. So the first move gives us a negative sign, the second move gives us a positive sign. So we have plus c squared dx wedge dy wedge dz. And factorizing the scalars, or taking out the common volume form here, putting it out here, leaves us with a squared plus b squared plus c squared dx wedge dy wedge dz. We can just see that's the modulus of omega, the inner product of omega with itself, okay, squared, and times the volume form in R3. All right, first step there. So what we're showing is that omega wedged with itself will give omega squared here if there are constants other than 1, and times the volume form for that space. All right, we've seen that rule in a previous video. All right, so let's consider R4 with the metric G is now Euclidean space R4, 4 dimensions. So the metric is simple. It's the diagonal metric with the 1s in diagonal and 0 everywhere else. In special relativity, this would be -1 and then all these +1. So you'd have R3 plus 1 or 1 plus 3. You have -1 here and then +1s here. And in general relativity, this would be a negative with some function of coordinates, and similarly over here, something. But positive, sorry. At least for the metric I use on this channel anyway. All right, so we have the 2 form omega is a dx wedge dy plus b dz wedge dz. The Hodge star of omega is, and again refer to the previous video for all this, omega star is a dz wedge dw minus b dx wedge dy. So please have a look at the last video for that. Verification. So the volume form on R4, vol subscript R4, is dx wedge dy wedge dz wedge dw. It's the highest form we can have in 4-dimensional space. It has the 4 coordinates. And omega wedge star omega is this wedge with this. And again, we can a dx wedge dy with a dz wedge dw. So we get a here and a here gives a squared dx wedge dy wedge dz wedge dw. And then over here, the now a dx wedge dy with b dx wedge dy is no point there. That's just 0. So that's not included in the calculation. Then b dz wedge dw wedged with a dz wedged out. Again, no point. dz with dz is 0, dw with dw is 0, so there's no point putting that in here. I haven't even put zeros in here to demonstrate, just to save space. I've left it out. So the 0 terms, or the terms that result in 0, I've not shown here. And the only other non-zero one will then be b dz wedge dw wedged with b dx wedge dy, and the minus out front. So we get minus b squared, that, and that. Now notice this one is dx wedge dy wedge dz wedge dw, which is the volume form. And this one here looks close to that. We just need to translate it. And by doing that, what we can do is swap these. It's a single swap of these two forms. And what we get is this minus becomes plus. So we get plus b squared. All right. Doing that, we've now got, we can now take out the common volume form factor, dx wedge dy wedge dz wedge dw, and we have a squared plus b squared in parentheses. So this gives us a squared plus b squared in parentheses times the volume form in R4. All right, let's keep going. All right, let's find the Hodge star of dz wedge dw in R4. So dz wedge dw wedged with the Hodge form dz wedge dw is equal to the volume form dx wedge dy wedge dz wedge dw. The Hodge star of that is dz wedge dw is minus dx wedge dy. If I put in here minus this, then it'll be equal to this by one swap. That's why I need the minus there. When I swap it, so it looks like this with a dx and dy in front, this minus will change to a plus. In other words, that wedge that is equal to this because of the anti-symmetry property. Now, key point here, entire two forms move. When you just saw me do this two form here, okay, this is equal to this simply because I can move this whole two form in front here, and that changes the sign. So entire two forms move. So when both dz wedge dw and dx wedge dy are treated as single entities, the whole entity dx wedge dy moves relative to the position of dz wedge dw, right? So that moved to the front over here. So this bit, this two form, changes position by one move to this form here, which is why the sign changes. Swap, and since the permutation achieved this involves an odd number of swaps, in this case 1, it's an odd number, it introduces a negative sign. So the negative sign in the result comes from the fact that when you move dz wedge dw to the position of dx wedge dy, you're effectively doing a single swap of the whole two forms, resulting in a negative sign. Okay, but swapping that, or moving this one to the front, one swap changes the sign. All right, example, let's consider one form omega is f of xy, some scalar function f of xy dx plus g of xy dy on R2. Now the Hodge star of omega is f of x dy. Remember, dx, the Hodge star of that is dy, and the Hodge star of dy is minus dx, hence the sign. Remember, that was in the last video. That specific example was given. All right, let's verify that the omega wedged with its Hodge star is going to ultimately give us the volume form times some constants. Okay, so let's do omega, wedge it with its Hodge star, expand it out, so f of x dx, this one we get f squared, f times f is f squared of dx wedge dy, minus this wedged with this, hence a minus, so we get f times g, dx wedge dx, well, that's going to be 0. Plus then this one wedged with this one, so g times f dy wedge dy, well, that's going to be 0. And then this one plus g of xy dy wedged with minus g of xy dx. Okay, here we go there. That's dy wedge dx. So what we get here is this first term will survive, and this fourth term, the last term, will survive. These two are 0 because by the anti-symmetry property, dy wedge dy is 0. Okay, so f squared of dx wedge dy minus g squared of xy dy wedge dx. Well, dx wedge dy has the opposite orientation to dy wedge dx, But we can change that by the anti-symmetry property, and that we can swap these two. Put the dx first, but that'll change the sign out here as a single swap, one swap. So odd number of moves, odd numbers of permutations, change the minus by a sign to plus. F squared dx wedge dy plus g squared dx wedge dy gives us f squared plus g squared in parentheses. Common factor of dx wedge dy is f squared plus g squared times the volume form for R2. So that holds. Okay, so example, let's verify that omega wedge star, Hodge star of eta is the inner product of the form K-form omega with the whatever form eta is, times the volume form for R3, because we're just going to do this in R4. R3, sorry, my apologies. Holds for two one forms omega and eta and R3, so we're going to make them one forms in this example with the standard Euclidean metric in R3, which will just be the diagonal matrix here, with ones in the diagonal. So let omega be dx, a simple one, eta be dy. In R3, the Hodge star operator on a one form transforms it into a two form. Go back to the first video for this. Star eta is star dy, and as we found in the first video, that's dz wedge dx. Now compute the wedge product. Eta wedge star omega, sorry, wedge star eta is dx wedge dz wedge dx. Well, dx wedge dx, that's just going to be 0. Then compute the inner product, omega eta in R3, with the standard Euclidean metric giving the inner product of omega with eta is the inner product of these row vectors, covectors, row vectors, one in the x place, one in the y place here. So as row vectors, this is dx, so there's one in the x place, 0 for the y and z places. For dy, you've got 0 in the first place x and 0 in the last place z. Okay, so to evaluate that, that is the row vector metric transpose of this last covector here, and we get 1, 0, 0 in a product of that and that, which is 0. So we have the omega wedge star eta, the Hodge dual, Hodge star of eta, is equal to 0. It's equal to this because both sides are equal to 0. We found that this product here is 0, and we found that this inner product here is 0, which means that this left-hand side equals the right-hand side, 0 equals 0. Now in this example, we used omega as dx and eta equals dy, which are orthogonal in the standard Euclidean metric. The wedge product, omega wedge star eta, and the inner product both evaluate to 0, consistent with this formula. All right. Let's move on. Let's consider another case in R3 with omega is x dx plus y dy, and eta is y dx plus z dz in R3. Step 1, compute the Hodge star of eta. So Hodge star of eta is y star dx plus z star dz. Well, as shown in the first video, that's equal to y dy wedge dz. So the star of dx is dy wedge dz, and the Hodge star of dz is dx wedge dy. So star eta, or the Hodge star of eta, is y dy wedge dz plus z dx wedge dy. Next step, compute the product, omega wedge star eta is that, wedged with that. And expanding all that out, so we've got this x dx wedged with this 2 form, and then x dx wedged with that one. Then y dy wedged with that 2 form, and y dy wedged with that 2 form, and you're going to see sum of 0. So writing them all out, here we go. Look, dx wedge dx is going to be 0. Dy wedge dy will be 0. Dy wedge dy will also be 0. So second, third, and fourth terms are 0. The only one that's non-zero is this first one, x. So let's take out the scalars, x, y out front. Dx wedge dy wedge dz, plus the others are 0, and that just leaves us with xy dx wedge dy wedge dz. All right, then next step is compute the inner product, omega with eta, inner product, so that's these covectors. Remember x, y for the first one form, and then y, z for the next lot. And when we compute that inner product, we'll have x, y, this, and this. And we will have this transpose, so y 0, z, x, y 0, because remember we had x dx, y dy. This one we had y dx and z dz. Okay, when we do that, we'll have x times y, but y times 0 is 0, 0 times z is 0. We're just left with xy. Okay, then next step, compute the volume form on R3. Well, volume form on R3 is just by definition dx wedge dy wedge dz. Then verify both sides. Omega wedge star eta is xy dx wedge, remember that? And this here, if you remember, was we found the inner product omega eta to be xy, and then the volume form is this. So you can clearly see that this left-hand side of the formula agrees with the right-hand side. And that's it. We're finished with this video as well. I hope everybody's happy with that introduction to the Hodge star operator over both this video and the previous one. I hope you find them useful and helpful in getting you started with this object. And I look forward to seeing you in the next video. All right, everyone, take care. Thank you very much. Bye.